Hello everyone, we meet again. In the course of Principle of Electric Circuit 2, we will introduce you two kinds of energy storage components, which are capacitors and inductors. Then we will analyze circuits containing energy storage components, that is, dynamic circuits, from the perspectives of time domain and sinusoidal steady states. You will find quickly that dynamic circuits can provide richer functions than resistive circuits, so the course of the second part will be wonderful. Let's begin. Before the discussion of the dynamic circuits, we need to introduce and analyze two most basic elements of dynamic circuits, that is, capacitors and inductors, in detail. First, we introduce capacitors. We assume such a scenario. The top is a metal plate with size S. The positive charges stored on it are plus Q. The bottom is also a metal plate with the same size S, and there are equal amounts of negative charge stored on it. Assuming that the plate area is big enough so that the charge is uniformly distributed on the plate. At the same time, because we ignore the edge effects of the plate. So according to the electromagnetism, we know the presence of electric displacement in such a medium. In such a boundary, we take a section. According to Cousin theorem, we know that is equal to the charges on the plane. That is, for such a homogeneous field, it is d times delta S. So we know that d equal to Q over S. We also assume that it is a linear homogeneous medium, so we get the electric field intensity E equals to d over epsilon, and according to the definition of electric field, we know that the voltage is the integral of electric field intensity. So the expression of U is this. In the case of a homogeneous field, U is equal to E times D, where D is the instance between the plates. So we got U, voltage U. Through the above analysis, we found that as long as there are charge exists, they will produce voltage U. So we can further define a new quantity. That is, C is defined as Q over U. So it's equal to epsilon S over D. The above derivation gave out the most fundamental expression of the flat capacitor. Many practical capacitance calculations are got by this fundamental expression. Before we discuss the other contents, similar to resistors, it should be noted that capacitors may be our special implemented devices, but they may also be parasitic parameters of some electrical characteristics. Fabricated elements need to meet the predefined capacitance value. Parasitic parameters might cause problems for electrical characteristics sometimes. It need to be overcome and solved. After having the definition of C equal to Q over U, let's discuss a capacitance value. Its unit is farad. The common used ones are microfarad, picofarad, and nanofarad. After knowing the relationship between the electric charge and the capacitor and voltage, and the current is dq over dt, we can derive that I must be equal to C times du over dt. If the capacitance is a constant value, This expression is the differential relationship between the voltage and current on the capacitor. By the expression, we can see that if the voltage is a constant value, the current must be zero. What does that mean? For a DC voltage, capacitors are equal to the open circuits. In addition to the differential equations of voltage and current, we can derive the integral equation between them. That is, U is equal to 1 over C times the integral of I. We put the integral into two segments, from negative infinity to 0 and from 0 to t. For this part, we define it as UO, U0. You can see the difference between capacitors and resistors from here. It must be U equals to R times I for resistors. That is to say, the voltage changes immediately once the current voltage changes, but for capacitor itself, it's able to remember the voltage at 0 times 0, but it also considers the change of the current after moment 0. It is the role of storage. Of course, it can store either energy or storage or signal.